Okay, without further ado, here is Josh Doman, who's going to talk to us about trusted execution.
Thank you. All right, hello everybody. I'm going to be the last talk, so I hope we get some energy. I'm going to try to get people involved, and we'll be definitely encouraging questions during the talk. So whoever has the microphone, just make sure people know where it is. I will be presenting. So I'm an independent developer based in Atlanta, Georgia. Yeah. And I'm going to be presenting Confidential Script, which is a new project I'm working on designed to emulate some of these proposed opcodes that we've been talking about, covenant opcodes, the CAT, etc., using something called trust execution environments, or TEs. I'll talk about what that looks like. It's not entirely new idea, but this implementation. So to get things started, what's the problem? Well, soft forks are really, really hard. Building consensus around new software proposals is nearly impossible to do today. There's always developers, they're advocating for new functionality, they want CTV, they want CAT, there's simplicity, there's things like CCV. But there's not really a clear leadership or consensus process to get these adopted, and it's really difficult to build momentum. And what you basically have is what I would describe as a chicken and the egg problem, because the best way to prove demand for this functionality is through real-world usage, real applications. But you can't get real applications or real-world usage without activation. And at the same time, users are understandably very wary of unintended side effects from activating these proposals. You're worried about MEV and centralizing mining, worried about things like inscriptions and things like that came out of Taproot. And so you really have what I would describe as fundamentally a governance problem. And so at the base level, the question is, how does Bitcoin adopt contentious new functionality? There's currently things on the table that's very contentious, but there will be functionality 10, 20, 30, 50, 100 years from now that will be just as contentious as what we're dealing with today. So what is it that developers want to build? We saw some of that earlier today in some of the earlier talks. This is just not an exhaustive list. Some of the projects that I find most exciting, things like Shielded CSV, which is a project designed to enable almost perfect privacy and better scalability of Bitcoin with unilateral exits. Some things like some of these ZK programmable L2s to be able to do lending protocols and AMMs and have much more secure bridging. Vaults, as some people we talked about earlier, more secure custody, mining payout pools, to be able to have better decentralized non-custodial options. And you can see the kinds of functionality that the developers are demanding so that these types of applications can become possible. And please stop. If everyone has any questions, just raise your hand and we can stop at any point. So what are some existing strategies that exist to adopt new functionality? So on the top left, we've got the benevolent dictator. All right, we all want this at our heart, right? We want somebody who's going to stand up and lead and tell us this is what we're going to do and just pushes it forward and everything's nice and easy. This is what Bitcoin used to look like in the earliest days when you had Satoshi and maybe Gavin and some of the early Bitcoin core developers. We're not ever going back to that world, especially after some of the lawsuits. The core developers, they don't want to be seen as being responsible for changes to Bitcoin, as being responsible for Bitcoin, let alone be responsible if something were to happen that was not, that people wanted to sue over. They don't want to be seen as taking on a lot of risk, but pressing the merge button to put it into Bitcoin Core. Then you've got the contentious activation client. So this is when some developers, anonymous or not, fork Bitcoin Core, where they activate the proposed functionality and they try to get the users to adopt it, start running it, and basically force everybody else to go along with the proposal. To some extent, you could say things like SegWit might fall in this category. I don't know if you would really say Taproot would, because, but that was before my time, really. But then there's another option which has been proposed. It's called the Core Untaught Software proposal. I'm not going to go too much into it. This is Paul Storr's proposal, where you don't. It's basically the contentious activation client, except you keep using the Bitcoin Core software, and then you run some extra software on the side that implements the soft fork. And then finally, you have the testnet or the sidechain first approach, where you say, hey, you want to build this new functionality, you want to build this bridging, cool. Why don't you prove it out on testnet with fake Bitcoin, or prove it out on a sidechain like Liquid? This is okay, but it doesn't really help because people want to be using real Bitcoin, and you don't really learn a lot about the game theory of adopting this functionality if you're doing it on a sidechain or on a testnet. And really, like users want to users want the trust assumptions of Bitcoin. They don't want to be having to make the trust assumptions of a federation. Yes, Evan.
Is there an example of a testnet first or sidechain first approach?
I mean, obviously, arguably, every soft fork that's ever happened was first on a testnet, right? I would say that in the current era where soft forks are extremely contentious, there's no feeling, I think, among developers that spending millions of dollars building these complex systems on testnet is going to really significantly move the needle in getting something like CAT or something like even CTV adopted on mainnet. At the same time, other developers who are more cautious of these things, that's what they say. They say, hey, we're not going to even consider putting into Bitcoin Core until you have proven out the code written on testnet. So I would say that that's currently what developers advocate, but I also don't think that you're going to find people spending millions of dollars investing in testnet first solutions that may never see the light of day. Cool?
Yeah.
All right, great. Thank you for the question. So the approach that I'm going to be talking about today, I'm calling the emulation first approach. And this is where you build real-world systems that use real money with the exact same code that will be run when the soft fork gets adopted, using a trust minimize signing service. And I'll get into a little bit what that looks like. But again, the big difference here is rather than having to write a bunch of code for testnet that will never actually be used by real users with real money, you can write the same code that you'll use when the soft fork gets adopted, and you just have a trusted signing service that you have to use in the meantime. This is not a new idea. It has been discussed before. Jeremy Ruman talked about this specifically for his CTV proposal. The Taproot Wizards guys are talking about something similar for CAT. Arcade is also doing some interesting stuff. But nothing's currently live that implements this approach. So like a super high level, what is emulation? You start with a emulated transaction. You pass it to this secure signing service. We'll talk about how that could work, which will then validate the emulated transaction. It'll say, hey, this is a valid transaction according to our consensus rules, including the new rules with the new functionality, CTV, CAT, etc. And if it's valid, we'll then produce a signed transaction that's valid on mainnet, which you can then broadcast and use, and will be valid. And so the fundamental question I'm asking is, how trust minimized can we make this signing service? How permissionless can we make this? How close can we get this to the gold standard of Bitcoin today? We'll never be able to get to perfect trustlessness, but how good can we do? So one of the key ideas that I'll be using in this talk is Taproot. Just by a show of hands, who's here is familiar with Taproot? Taproot. Okay, seems like about half, 2/3. So super high level, Taproot was adopted, I believe, in 2021. One of the main functionalities of Taproot, among others, is it has two different spending paths. So on the left, you've got the key path spending path, which is the simplest, literally just a key, and you make a single signature, and that's how you can spend funds held at the Taproot address. And then the other way that you can spend is called a script path. And script path supports much more complex spending conditions using Bitcoin script. And you essentially have this Merkle tree. You can just think of it as a tree, as you can see on the bottom left. And at the bottom of the tree, each leaf is a different script. And you can select the script that you want to use, and you can provide the conditions necessary to make that script valid, and then you could spend from the address. So in this project, what I do is we say, okay, first we want to validate a script path spend. Then we're going to want to derive a private key from the Merkle root, which is right here at the top. And then we're going to use that key to then key path sign the real transaction. So in short, we're going to be converting script path spends to key path spends. I'll go over this again once we get to the actual implementation. So what the goal is to make emulation as close to trust minimized as possible using a technology called TEs, or Trust Execution Environments. We'll get into that in a second. The goal, though, is we want to minimize the risk of theft. We want to eliminate operator lock-in so that you're not dependent on a single operator to be able to emulate your transactions. You should be able to emulate your own transactions, actually. And we want to be able to maximally protect against the loss of key material. And the goal is so that developers can invest resources to build production-ready, user-friendly systems using this new functionality, the things that people are talking about. And those things will operate as written once the soft fork is deployed. So when people deploy the soft fork, you literally just run the same code, and you'll be able to use whatever system you built. So a trust execution environment is not necessarily a new technology, but it's definitely matured a lot in the last couple of years. At a high level, you can think of it as like a super special lockdown black box that's totally isolated from the outside world. It segregates all the memory in the CPU from the external environment, such that you can run code inside of it, and the memory inside of the TE wouldn't be accessible to an attacker running some software elsewhere, or ideally even a physical attacker. And at the same time, being able to provide secure attestations about the code being run inside and the results of any of those computations. So a really good example, anyone here is familiar with Phoenix Wallet? It's one of the probably the biggest Lightning LSPs and just ways that people access Lightning. Well, they are a major user of TEs. They use AWS's Nitro Enclave, which is one of the most mature solutions out there on the market. And they're right on the homepage if you go to look it up, AWS Nitro. And they use it to run all their secure all their funds. Other options exist though. Intel has one, AMD has one. In this talk, I'll be talking later about using hyperscale providers, just because while TEs are super secure, it's really difficult to guarantee that a physical attacker can never try to break inside and get into any secrets. But if you're using a hyperscale provider, you have a little bit added layer of trust. They provide some physical protection. So the first project that I built, which I put on Delving back in August, is a Rust library called Confidential Script Live. And it's a totally abstract library. It's independent of any TE implementation. And it specifically just allows you to emulate Bitcoin script by converting script path spends to key path spends using an abstract quote-unquote verifier. It's designed to be able to be used inside of a TE, which is going to be preloaded somehow with a master private key. And then you can use any verifier that you want running any fork of the Bitcoin kernel, for example. The Bitcoin kernel project is a really exciting new project that allows you to run this same consensus code in Bitcoin Core outside of Bitcoin Core. And so you can essentially run the same kernel, or you could run a fork of the kernel that implements opcat, opcdv, whatever simplicity, whatever new functionality you want to provide. Yes?
Bitcoin kernel just hit 1.0. So did you build this on a pre-release version?
Yeah, that came out yesterday. Yeah. So yeah, this is built with 0.0.0.22.
Very cool.
Yeah. But yeah, so the Bitcoin kernel just officially got merged into Bitcoin Core, which is a huge deal. And yes, there's now a 0.1 version out there. The other thing that I want to talk about, and I'll get into a little bit, is this library supports offline address generation. So you'll be able to generate addresses to spend funds to without having even to interact with a TE running in the cloud somewhere. And then everything is deterministic in terms of the derivation of those keys, which I talked about previously. I don't want this to feel too intimidating. I've been told it can feel intimidating. So I'm going to try to keep it at a very high level. We want to just generate an address. We want to know, like, hey, where do I send my funds to? Well, we can get from the TE a master public key. That's totally safe for us to have. Then from the master public key, we can then derive a child key from the Merkle root of all the scripts that we want to allow ourselves to be emulated. This will then give us what's called an internal key, which is what we need for Taproot. And then finally, we can either use that internal key by itself without any scripts, or we can add additional backup scripts. So these will be real Bitcoin scripts that are not emulated, which might have time locks, other things that allow us to spend the funds in the event that for some reason we can't emulate the transaction. I'll stop there. I can repeat that if people are following. I don't want everyone to get lost. Yes.
Thank you. So if you current Taproot, the thing that you've added that's different is the emulated Merkle root. Does that make sense? Because normally you got your public key. Oh, this is from the T. Okay, maybe I'm like slightly. Because normally you have like your external key. So normally with just Taproot, you maybe have the far right side. You'd have your internal key,
Yes.
and you would have your Merkle root, and
Right.
then those combine together to create your public key.
Mhm.
And so for this, you've taken those two pieces on the far right, or the normal Taproot pieces. You've added like two steps in the middle. One where your master public, you've got like this key from the trusted execution environment, and then the option to add an emulated Merkle root to that.
I think you got it.
Okay.
Yes. Yeah. Just to repeat that for everybody else, that's a good analogy. So on the far right, this is kind of the normal Taproot setup. Normally, you provide an internal key, and then you provide your script path, and that gives you your Taproot address. What we're doing is we're saying, okay, we're not going to have the user provide this internal key. We're going to derive it. And what are we going to derive it from? We're going to derive it from our emulated scripts, and we're going to derive it from the public master key, which is inside of the TE.
So you've kind of like nested another layer of public key and a Merkle root that you tweak together, and then that becomes the internal key that you add into the existing Taproot structure. Okay, that's very useful. Thank you.
Yeah. There's another question back here. Oh, you fell? Okay, cool. All right, awesome. Yeah, I don't want anyone to feel like this is intimidating, but I've been told that this can be an intimidating slide. So for those folks who are familiar with code, this is actually what the API looks like in the library. Basically, all you do is you provide the public key, you provide the emulated Merkle root of the emulated scripts, you provide optionally the Merkle root of the backup scripts, and then what network that you want the address on. All the networks are available in Rust Bitcoin, so Bitcoin, testnet, Ignite, I imagine. So emulated spending, this is a fairly close analogy to what we saw on the previous slide. I'll actually go through an example in a second, but you start with providing a Bitcoin transaction that's going to have some emulated witness data. You can have some non-emulated inputs too that you don't want to emulate. Then you're going to provide that to your TE, which is going to hold some type of master private key, and it's going to validate the transaction. And if it's valid, it's going to replace the witness data with a Schnorr signature for a key path spend. So this is a toy example, but real transaction that I've emulated. So if you haven't seen what a Bitcoin transaction looks like before, this right here is the emulated Bitcoin transaction. You've got the version number, you've got the lock time, you've got the input data, like the previous output, the sequence number, etc. And then here we have a script path spend witness. This has two elements. It's just a really toy script, just an opt true. So you don't need any other elements. But this is what we're going to be validating, and this is what we're going to, if it's because it's valid, we're going to then sign. What we also have to provide are the actual spent outputs that we're spending. And these are required so that we can validate signatures, produce signatures, and also if we have any kind of introspection opcodes, that will allow us to do introspection. And then here are any backup Merkle routes that we have for backup spending. So right now, this example, we don't have any, but you can imagine you can put some here, and this will be your scripts in case you aren't able to emulate. Good question.
Okay, so the number 2 block, that would have covenants inside of it.
Yep. So this one doesn't, and this is just a opt true, but any script here, yeah.
Okay, so this would look like, just to verify my understanding, this would look like any complicated script that has covenants inside of it, identical to what it would be if the covenants were actually activated.
Correct.
Cool.
Yeah. So you could imagine this being huge potentially if you wanted to do like a giant Stark proof, for example. It could be enormous. But what we'll see in a second is it doesn't matter how big this is, if it's valid, this will be the result. So after we validate it in our TE, the TE will replace the witness with a single element, which will just be a Schnorr signature.
I'm still a little confused. So if it was an opt true, why is there all that gobbledygook? Is it a public key or?
What, here?
Yeah.
This is the control block.
Can you explain control block?
Oh, okay. That's okay. So in Taproot, the first element is going to essentially be the proof that the script is committed to. It's going to have the internal key that you're using, and it's going to have the...
Oh, so that's the Merkle root of the script.
Well, it's not exactly the Merkle root, but it's the information that you need to be able to prove the Merkle root is committed to.
I see.
Yeah.
I'm tap retarded.
In this case, it's super short because we have a single script. Yeah. Yeah. Well, yes. It is the root in this case. Yes. But normally it doesn't necessarily this. Cool. So this is what the API looks like. You provide this abstract verifier, which I'll talk about in a second. That's what's actually going to be validating, verifying the scripts. Then you're going to provide your transaction. You're going to provide the outputs that you're spending. You're going to provide some randomness. You're going to provide the secret, and then any backup Merkle routes you're using. And there's some details here I won't get into unless we want to at the end, just about how I'm treating annexes and other various edge cases.
Sorry, can you get back for a sec? Yeah, just to verify. Okay, so effectively what you've done is you've taken a script, a transaction that has a bunch of covenants in it, and you've converted it to something that just looks like a normal Taproot transaction with no covenants in it, that is indistinguishable from any other normal Taproot transaction.
That's right.
Cool. So
that's right.
And that's like the magic that the TE does.
Yep.
Is that it's able to do that conversion. So,
correct.
Okay.
So like it provides, there's some privacy benefits you could argue, because on chain people won't even know that it was an emulated transaction. It's just going to look like a normal Taproot key path spend. And there's some cost savings too if that was a very large covenant.
Cool. Thank you.
Yeah. Great. Good questions. This is the verifier API. So this is what we're going to be providing to the verify and sign. And this is what's going to be presumably implementing Bitcoin kernel, verifying, or fork of the Bitcoin kernel to be actually verifying the scripts. And it's just providing the script pub keys. and the transaction, the outputs that are being spent. And the library has a default implementation with a default kernel built in if you want to use that. So one thing that I'm hoping to do in the near future is add Musig2 support. So right now, Musig2 is a really cool new technology that you can use with Schnorr signatures to basically be able to combine signatures together and have two people have the ability to authorize a single transaction. This is going to be added to Rust Bitcoin hopefully shortly, and that will let us be able to add additional security for users who want that to the TE, where you can have maybe 2 different TEs and 2 different cloud providers verifying transactions, or a setup where you have a TE and the user both having to verify, but the user alone can't spend and the TE alone can spend. So you can understand how Musig2 could be really useful to giving whatever users the security that they desire, if they want more security than the base implementation. Great. So I'll pause there for any other questions, and then I'll get into an implementation that I've developed. Yeah, go ahead.
So in a basic example where 2 users are transacting, which of them needs to have access to the TEE's public key, if either?
Can you give me an example of how 2 users are transacting? Are you talking about just like a regular like a spender and a receiver, or like a shared UTXO?
So I guess if you're going to create an address that has covenants, and I'm taking, in this example, I'm taking just any arbitrary coins and sending them to you.
Mm-hmm.
You're creating the covenants address, and then you're sending them to a third person.
Okay.
Where in that that chain does someone have to have like the key from the trusted execution environment?
Got it. So in order to generate an address, no one needs to have any access to any environment, because all you need is the public key. Okay. So once the public key is out there and known, you don't need to even interact with the TE in order to be able to generate an address and know where to send the funds to. Then to spend from the TE, you will need to create a valid emulated transaction like this one. And then you'll either need to run your own TE, like go to AWS and deploy the instance and emulate it yourself. Or you'll need to send it to some servers that you might pay some money to emulate it for you. Or conceivably, you can just broadcast it on the internet, put it on Nostr or something. And if it's a fee-paying transaction, presumably somebody's going to find it profitable to just emulate it themselves. And so conceivably, you might not even have to run your own TEs or pay any money for it. It'll just be part of the fee that you're paying for your transaction. The miners will take care of it for you. The point, though, is that different users can run their own instances. They can emulate their own transactions, but other people can emulate transactions for you if you don't want. It's not a single operator necessarily, though, that you have to be working with. That's the goal. And I'll get into that in a second, how that might work.
Cool, thanks.
Can you go back to the slide with the combination key and trusted execution environment?
This one?
No, I think it was like one back from wherever the tip of the chain is. Forward. The Musig.
Yeah.
It's breaking my brain a little bit to think about this. So this is like a Franken transaction that combines a trusted execution covenant and a multi-sig covenant execution. Is that?
Yeah, so Musig, you can think of it as a scriptless multi-sig. That's kind of actually, I think, what people describe it as sometimes. And so it doesn't appear on chain. It looks like just a single signature. It's using some math magic. And essentially what you'd be doing is you would go to one TE, you would say, hey, emulate my transaction. I'm emulate my transaction. And it will say, great. But instead of giving you back a fully signed transaction, it will give you back part of the Musig2 result. And then you'll go to the second one and do the same. And then you'll be able to combine the results and get your actual signature. Sorry, you're a little quieter now. We lose power.
Like Arc today, it kind of emulates covenants with multi-sig. So this would be a similar. Yeah, I'm just like.
Oh, I'm not super familiar with Arc's setup. My understanding is they are emulating covenants, but they're only doing it on their layer 2. So they're not emulating layer 1 covenants. They're asking users basically to bridge into Arc, and then once it's in Arc, they're using their service to do a similar type of emulation, but only within the service. I think so, but I'm not too familiar with their service. I'm not sure though if you could do like L1 covenants using Arc. I think the covenants have to live within Arc. Yeah, that doesn't matter. But yeah, they're doing emulation stuff too. And so is Taproot Wizards. They're doing some stuff too. Cool. We have a little bit of time, so I have a working implementation, and if we can get the computer to work, I can do a little bit of a short demo. This is super still premature. It's running. I wouldn't encourage anybody to use it. Please don't. I don't want anyone to lose any money. I'm calling it pre-alpha, but the code is up on my GitHub. And it is an implementation of this library inside an AWS Nitro enclave, integrated with KMS, which is Amazon's key management system service. And it uses Nix to do reproducible builds so that you can get the same image hash every single time you build it. And that's what allows you to then be able to interact with KMS in a reproducible fashion. There's some details that I'm not sure we're going into. The master secret is automatically loaded into the enclave using KMS. So you don't really have to trust anything beyond Amazon's existing trust assumptions. The master secret also has the option of being further hashed with a timestamp from a Bitcoin block hash so that you can be certain of the key policy of the AWS KMS key. Right now, I have 2 versions. I have one version that's running using the Rust Bitcoin kernel, and I have a separate version that has a support for CAT, CTV, and CSFS. Credit to StuTXO for building Rust Bitcoin kernel covenants, but that's not peer reviewed, so please don't use it. And also has some basic DOS protections for successfully large transactions, and the optionality to encrypt data into and out of the enclave so that you have maximum privacy. Hopefully, my goal is for one day we have like a very standard place where we have covenants and opcodes and features implemented in ideally something like Bitcoin Inquisition, and there will be a kernel version of Bitcoin Inquisition that has all the things that people desire. In terms of like security and trust model, I guess there's really 3 aspects to it. You've got the reproducibility aspect. So that's where Nix comes in. Nix provides a much higher degree of reproducibility. So you get the same output, and you have certainty that the code in the enclave is actually doing what the people who write the code say it's doing. Then there is confidentiality. So you're going to have a lot more confidentiality potentially using this service because no one's going to know about it, unless, of course, the enclave gets broken somehow and the TE assumptions are broken, and people are able to extract the keys. That would be disastrous. Then there's availability assumptions. So Amazon had a big outage a couple weeks ago you may have heard of. So if there's a big outage, you're not going to be able to use the service to be able to emulate your transactions. And conceivably, you can even potentially get banned from AWS. Or if somehow this service was not considered neutral infrastructure, AWS could ban the entire service, anything that runs its image hash, which is why it's really important that it supports many different types of applications and not just applications that might be deemed more advantageous to bad guys. In terms of KMS, for people who are familiar with KMS, basically it has native integration with AWS Nitro, where you can basically define an AWS key such that it can only be accessed by an enclave running a specific image hash. It's relatively inexpensive. It's just about $1 a month per region for one of these keys. And so you can conceivably put up a couple $1,000, $2,000 into an account that you then make sure you don't have access to. And you can host a cross-account key that can be accessed by every single person on the planet as long as they're running this enclave. And you can even make this setup even stronger by making it so you have multiple KMS keys, and as long as one is alive, the emulated service continue to function. Some API usage. This is what it looks like. You first got to set up the enclave, and you provide the key that you want to use and the block hash that will timestamp the key. I know it's very impressive. Then there's an API to retrieve the public key that we can use for offline address generation. And this is the API to be able to emulate a transaction. This will probably change in the future, but you provide the emulated transaction and the outputs and the Merkle root that you want. And essentially what you get from this is the ability to emulate your own transactions just by running your own instance. So you don't need to go to a designated emulating service to be able to emulate your transactions. You can just spin up your own instance, send your transaction to it, and as long as Amazon AWS is in existence, you'll be okay.
Wait, so question. So you're saying that I could use the TEE with like some service, you know, that like it supports my wallet, for example. They could like use their like Nitro Enclave to create my transactions, and my coins are locked in this vault that they control. Then they can like go out of business, and then I can spin up my own server and still like recover my vault.
That's the goal.
Wow.
Yeah, but the way that has to work is you would create a cross-account KMS key in its own like single-use account that then cannot be accessed thereafter, and you pre-fund it with enough funds so that it basically is alive for a very long time. And yeah, if they go out of business, you'll be able to still access your funds because you can just run your own instance. Yeah. That's another backup, again, in addition to the script path backup that we talked about earlier. Use cases, like Ty talked about before, vaults, ZK rollups, things like shielded CSV, some more private C when you're on L1 because everything looks the same, mining payout pools, sequenced AMMs, etc. I would really kind of on the sequenced AMMs point, I think it's worth touching on. I think it's important to acknowledge that with any of this functionality, the risks that people are worried about would still be applicable. So if you're worried about things that have recursive covenants introducing MEV, conceivably the MEV will be introduced through a service like this. Is that bad? I don't know. I mean, it's technology, and this is what the technology enables. And if it's going to happen through a service like this, we'll have to develop the solutions to mitigate it regardless. And so part of the motivation for this a little bit, beyond the ability for people to be able to start using this functionality today, is to push the conversation beyond like, hey, we need to stop the MEV because something like this is going to mean that the MEV might be coming regardless, and we'll need to develop solutions to mitigate it. And at that point, it reduces the actual riskiness for the core developers to press the merge button because we'll have to take care of it regardless. So, but yeah, I just want to acknowledge that like this is scary for a lot of people. Next steps. Yeah, want to get a peer-reviewed kernel implementing some of these opcodes. I want to make the UX of actually launching using the enclave much better. I want to add some documentation. Music too would be a great thing to add. So various things I'm hoping to do. I don't know if we have enough time to do a short demo. Do we want to do a short demo? Yeah? Okay. Okay, well, this is a Telegram group, by the way. If anyone wants to follow along to the project, I'll be posting updates in there. And let me go. Oh, perfect. All right. So can we see this? All right. Should I make it bigger? Okay. Can you hold this? Thank you. All right. How's that? Yeah? All right. So right now I just am SSHing into an EC2 instance that I already set up. An EC2 instance on Amazon that's running, that supports Nitro. And I'm going to create come in it twice. So the first thing I'm going to do is I'm going to turn on the enclave. So it's spinning up the enclave right now. It's connecting to KMS, and it's all set up. So the next thing I'm going to do is I am going to set up the enclave with my with the master private key. So this is the API call we talked about earlier, where we have here the KMS key we'll be using and the block cache that timestamps it. Great. So now what it's just done is it's pulled in the key from KMS and loaded it into the enclave. We can, if we want to, get the public key, but for sake of time, I'm just going to emulate a transaction. So I have here the transaction that I put on screen, the little demo transaction. And we're going to emulate it. Great. Look what we got. We got our real transaction back. And if we want to make that prettier, we can go to here and we can, there we go. So now, yeah, so now you can see this is our key pass signature. So that is how you would use it without any GUI or anything like that, but currently running in Nitro, and hopefully within a couple months will be something that is production ready. So thank you so much. Yeah, any last questions?
Josh, have you seen any institutional interest?
I haven't really been publicizing it too much, but I published it on Delving back in August, and some of the folks at Blockstream thought it was pretty cool. I mean, I think simplicity is honestly perfect for this, because with simplicity, you'll be able to basically have any functionality that you could imagine. It just might not be as efficient as you might like. So you'll be able to have a single enclave that could be used for. But no, I haven't yet really publicized it too much. I'm still been building it. The RK guys reached out to me. They thought it was cool. I mean, I would love for some of the folks in the industry to take an interest in this. That's the goal.
Big fan of this permissionless, just build it and we'll figure it out later approach.
Thanks. Okay, well, thank you so much.
Thanks again, Josh.